So first things first, what actually is a capacitor? It's a passive component that temporarily stores electrical energy and then releases it when the circuit needs it. You can think of it as a tiny, super fast rechargeable battery, except instead of chemical reactions, it works purely with electric fields. It charges up almost instantly and can discharge just as quickly. Now let's look at the two most important properties you always need to check when you're picking a capacitor. Number one, capacitance. This tells you how much charge the capacitor can store for each volt applied. The unit is the farad, named after Michael Faraday, but 1 farad is actually a huge amount of capacitance. Way too big for most electronics. So in real life, we almost always use microfarads. That's microfarads, 1 millionth of a farad nanofarads, nanofarads, 1,000th of a microfarad, and picofarads, 1,000th of a nanofarad. You'll see markings like 10 microfarads, 100 nanofarads, 47 picofarads. Those are the everyday values. Number two, the voltage rating. This is the maximum voltage the capacitor can safely handle before the dielectric insulation breaks down and pop. You might get smoke or a bang. Always choose a capacitor whose voltage rating is comfortably higher than the highest voltage it will ever see in your circuit. A good rule of thumb is at least 50% higher, or even double in sensitive or high reliability designs. Okay, how does a capacitor actually work? Picture this. Inside there's two metal plates, or conductive surfaces, facing each other but not touching. Between them is an insulating material called the dielectric. It could be ceramic, plastic film, mica, air, or even a very thin layer of oxide in electrolytic types. When you connect a voltage source, electrons rush onto one plate, making it negatively charged. At the same time, electrons are pulled away from the other plate, leaving it positively charged. That separation of charge creates an electric field across the dielectric. And that's where the energy is stored. No current actually flows through the capacitor itself. The dielectric stops it. But during charging and discharging, you do get a brief current in the wires as the charges move. Now let's quickly run through the main families of capacitors you're likely to meet. First up, electrolytic capacitors. These usually look like little metal cans with a plastic sleeve. They're polarized, which means they have a clear positive and negative side. Get the polarity wrong, and they can fail dramatically. They give you a lot of capacitance in a small package. Think 10 microfarads all the way up to thousands of microfarads. That's why they're favorites in power supplies to smooth out ripples and hold energy during brief dropouts. Next, ceramic capacitors. These are usually small, flat discs or tiny surface mount rectangles. They're non-polarized. You can connect them either way. They typically have lower capacitance values, from a few picofarads up to maybe a few microfarads in the bigger ones. They're excellent at high frequencies and very stable, so you'll find them all over RF circuits, decoupling spots next to microcontrollers, and timing circuits. Then we have tantalum capacitors. They look a bit like tiny dipped beads or small rectangles, often with a stripe or notch showing the positive side. They're also polarized. Tantalums give you good capacitance in a very small size, plus excellent stability and low leakage. The trade-off is they're more expensive and can fail dramatically, sometimes with flames, if overvoltage or reverse polarity hits them. So they're common in precision analog circuits, military gear, and medical devices where reliability really matters. Alright, what do we actually use capacitors for in real circuits? Here are the big three jobs. First, energy storage and smoothing. In a power supply, after the rectifier turns AC into pulsing DC, we put a big electrolytic capacitor across the output. It charges up during the peaks, and then feeds energy to the circuit during the dips. That smooths the voltage so your microcontroller or audio amp doesn't get annoying hum or glitches. Second, timing. Pair a capacitor with a resistor, and you get the famous RC time constant. That's how you make an LED blink slowly, create delays in 555 timer circuits, or generate the timing pulses in many classic oscillator designs. Third, filtering and signal coupling. Because capacitors pass changing voltages, AC, but block steady voltages, DC, they're perfect for coupling audio signals from one stage to the next while blocking any DC offset, bypassing high-frequency noise to ground. That's the decoupling capacitor you see right next to every IC power pin, and building high-pass or low-pass filters to shape frequency response. So there you have it, capacitors in a nutshell.